In the previous lecture, we talked about the forces that are acting on a hanging mass that is spinning around. I show an image here from the reference frame of a camera. This is taken from a camera that is watching this mass spinning around. And if you'll recall last time, what I talked about is how we have three forces acting on this mass. Let me draw them here. We have a spring force that is aiming inward, that's keeping it in its orbit. We've also got force 1, that is the strings pulling up on it, and we have F sub g, the gravitational force pulling down on it. Remember that these two forces, this one and this one, are balancing each other. That is, they have equal magnitudes. We know that because this mass is not accelerating up or down. This force, however, the spring force, is not balanced. Therefore, it is causing this mass to accelerate or to change its momentum. So the question that we want to ask now is, how can we use Newton's second law to relate the force and the change in momentum? You might remember Newton's second law states that the change in momentum of an object is equal to the net or unbalanced force acting on it times the time interval, delta t, during which this force acts. So what we're going to do is we're going to see if we can compute the change in momentum of this mass during a certain time interval and see, does this formula work? Okay, so what I'm going to do is so the question is, can this formula correctly relate the change in momentum of the hanging mass due to the unbalanced force F sub s acting on it during the time interval delta t. Okay, so that's the question we're asking. So what I'm going to do is I'm going to draw a picture here. This is a top view of this mass moving in a circle. Okay, so let's suppose that at a particular moment in time, the mass is right here. This is at time, let's say time t1. And I'm going to draw a line here. This is a suggestive line. And a little bit later, so if there was no inward force, if there was no spring force acting on it, then it would just move in a straight line at a constant speed. So it would fly out sort of in this direction. But the spring force is pulling it inward. So we've got the spring force pulling it inward, which is going to deflect it. So instead of going in a straight line, that mass is going to end up over here. So it moves along an arc instead, okay? So it moves along this arc instead of going in a straight line. The spring force provides this deflection inward, okay? Now, what I want to do is consider a very small time interval during which this moves through an angle theta. So during time interval delta t, the mass moves from position 1 to position 2. So here's position 1 at time 1, and here's position 2 at time t2. So delta t is going to be the difference in time, t2 minus t1. Okay, and during that entire time interval, this force, the spring force, is acting on it. Okay, so this is the spring force that is acting on it during this time interval. And what we want to do is, if we know this spring force, how big it is, because we've measured the spring force when it's stretched by a certain amount, and we know some time interval we're considering, can we find out what the change in momentum is during that time interval? So let's suppose we take, we know from timing this going around, so we know, whoops, so we measured the time for 40 orbits. So that allows us to measure the time for one orbit. All right, so we know the time it takes to get around once. So let's suppose we wanted to find the time it takes to move 1 degree. So if we know the time it takes to go around 360 degrees, so that's 360 degrees, so we can find or deduce the time delta t for 1 degree. Right? So we can find that time that it takes to move 1 degree. So we're going to be able to get this delta t. Okay, so we're going to be able to find that from the time of one orbit. We can find the time to move 1 degree. Now, if we know the time it takes to move 1 degree, we can get this quantity right here. If we've measured the spring force, we can get this quantity right here. Now the question is, what is the change in momentum? So what is delta P? What is the change in momentum during this time interval? Well, let me draw another diagram. And this other diagram is going to show, this is not a free body diagram. This is a diagram that's meant to describe the momentum of this at time 1. So it's going in this direction at time 1. And a little bit later at time 2, it's going in a different direction. It's going sort of tangential in this direction, right, at that particular instant. Now, this mass is not speeding up or slowing down. So what I'm going to do is just draw another arrow here. That is the momentum at time 2. So the momentum at time 1, P1, is going to be equal to the momentum at time 2, but they're going to be in slightly different directions, right? And the difference in direction is really the change in momentum. So if I draw another line right here, this delta P represents the difference in momentum between the momentum at time 1 and the momentum at time 2. That's what we're going to try to plug into here to see if these sides are equal. How do we figure out how big this change in momentum is? Well, let me just remind you, when you have a triangle and you know 2 sides of it, you can find the third side as long as you know the angle theta. How do you do that? Well, we know that angle theta here is going to be the same as the angle theta over here. That angle theta is going to be the same as that angle theta right there. And if we know that to be 1 degree, and we know that these 2 sides of this triangle have the exact same length, because after all, this isn't speeding up or slowing down, then we can find out what delta P is. So using the properties of an isosceles triangle, we can find the change in momentum, delta P. So that's what you're gonna have to do. You're gonna have to, using the momentum initially here, and by the way, we know the momentum 1, which was equal to momentum 2, which is equal to the mass of the hanging mass times its speed. So you're gonna need to know its mass, and you're going to need to know its speed, v, in order to do this. How do you find its speed? Well, you can get that from, we know how much time it takes to get around this orbit, and we know the distance it goes in one orbit from the radius of the orbit, so we can find the speed. So we can get this from the radius and hence the circumference of orbit and the time of the orbit. Okay, so then you can calculate your delta P, you know your delta T, and you can know what your force is, right here, the spring force, and so you can plug those in and see if you can find whether that formula holds. And that would be a Newton's second law analysis of this experiment.